Okay, so I'm going to record over the video because the voice didn't get captured after we did the HITT clicker question. So now we come to chapter 17, and this chapter is conceptually harder, but it is easier mathematically. So I'm going to go quite slow today and give you an introduction to the first section of this chapter, and hopefully it will not confuse you. So we're going to learn about electric potential energy, and we may or may not come to the potential difference today, okay? And then a little bit later on, we'll learn about how that electric potential is related to the electric field, and then go further in this chapter. So if I tell you that the electrostatic force is a conservative force, what does that mean? Do we all understand? Does it sound familiar? Right. So what it means is that if you have a conservative force field, then at every point in this field, you can define a value. So if you have some kind of sensor or measuring thing and you put it at different points, it's going to give you a different number, like 10.5, 10.7, 7.1, etc. And the numbers don't have to be unique. So that's the electric potential, okay, if you have a charged field. On a gravitational field, that varies by height. So just along the z-axis. So here you might have a height of 1 meter, 2 meters, 3, 3.5, 4, 5 meters, let's say. Yeah. So if you put your sensor at different points, you're going to measure something that's related to the location there. Yeah. And so for every unique point, we can define a potential and therefore a potential energy for the configuration in this field. What does that mean? That means that, let's say we look at the gravitational field first. This is also a conservative field. You learned about this in Physics 1 already. Therefore, I chose to start with this. So this should come quite easy. And you can use this diagram to help you figure out what is unique about a conservative force field. So in a conservative force field, let's say this is the ground, yeah? And I lift an object up from the ground from here to there, yeah? Let's maybe annotate. So from this starting position, I lift it up to this position B. Then at B, we know it has a certain amount of energy. We call that potential energy. So this is the potential energy, you know this formula mgh. How do you arrive at this formula? I did work. That work is stored in the form of energy up here. So what is work? How is work defined in physics? So work is actually force and then a dot product with displacement, which can be written as d or delta x, yeah, where d is this distance from A to B in this case. What is my force? My force must be at least mg for me to counter gravity, yeah, the pull of gravity beneath and the applied force upwards. So let's write that as some applied force upwards. And then times the displacement, and they are parallel to each other. So that takes care of the cosine theta that would have been required in the dot product. So I can write that distance d as my height h between A and B, yeah? So this is the work done in lifting an object from A to B, and that's equal to the negative of the potential energy, okay, by definition. Potential field, gravitational field, and this is the electric field. Here we have two metal plates, yeah, A and B, on which we have some charges. We call this a capacitor. So we will learn about capacitors later on, but we've seen this kind of diagram before, yeah, where we have this thing in red. What's in red? What's in red between the two charged fields? That's the electric field in red, and it's uniform. You can see that it's uniform, right? So we will place a test charge in here in a minute. But in this gravitational field, we have put two objects, and one is double the mass of the other. So this is m, this is 2m. Then you see that just with the formula, the one that's more massive is going to have more energy, right? It's twice mgh here because of 2m. So this is just what we saw before. Work done is equal to mgh, and it's the negative of potential energy. How do you open out a delta in physics? The delta U equal to UB minus UA. Negative sign, negative delta U. So negative sign multiplied by everything in the parenthesis is going to give me negative UB. And then I'm just going to move the second term first because it's positive now. Negative times negative makes positive UA. And that's what gives us what's up here, that the work done equals UA minus UB. So now let's come to the electric field. Yeah? And so we have a slight separation by this distance d. In this electric field, we have a set of charges here. The electric field lines are moving away from the positive, and they're arriving at the negative, right? That's how our field goes. So let's say in this electric field, we place a test charge, a positive test charge plus Q. What's going to happen to it? If we just place it there, what is it going to do? So the positive test charge is going to move from the positive side to the negative side because the positive forces repel it and the negative charges attract it. Yeah. So it's going to move this way. We're going to see that in order to move, it has some kind of energy. What kind of energy does it have? What's the energy associated with motion? That's the kinetic energy. Yeah. So for it to get kinetic energy to be able to move, it must have had some energy in this position, which it can then transform into kinetic energy to be able to move. Yeah. So the energy that it had by virtue of being here is what is called its potential energy. And its potential energy is very high just now, close to the positive charges, and it'll become lower as it moves to the other side. So left to itself, everything will want to move to a lower potential energy position if it can, okay? So it's going to try to lower its potential energy by moving to this side. So we have A side at high potential for a positive charge and B at low potential for a negative charge. Yeah? High potential energy over here and low potential energy over here. Yeah? We have to be careful that we are talking about a positive test charge because we could have put a negative test charge and then it would be different. And so let's see what happens if I put a negative charge there. So if I put a negative charge, now what is it going to do? If I just leave it, what's going to happen to it? And what we find is that it's going to stay right there by the positive charges. It's not going to move because it likes that position. This must be its lowest potential energy position. Yeah? So it's completely different, the behavior of a negative charge and a positive charge when I put them in the same field. Yeah. Okay, down here we have exactly similar stuff to what we have there. It's analogous. So we have work done equals the dot product between force and displacement. Force in an electric field is our electric force. And that by definition is equal to electric field times Q because we define the electric field. E is my E. Yeah. So force per unit charge gives me electric field. That means electric field times the charge is going to give me the force. Yeah? So this portion here is the force. and then multiplied by the displacement. And then the rest of this is exactly what we saw before. Okay, so we saw this, again, we talked about this before, just like for in a gravitational field, the bigger mass is associated with greater amount of energy, potential energy, written here. Similarly, the bigger charge in an electric field is associated with greater amount of potential energy. Yeah? The potential energy equals QE times D, QE being my force, D being the displacement. Okay, so in any conservative force field, yeah, the law of conservation will apply. Since there's no dissipation, there's nowhere else for energy to go. So whatever energy you start with, your initial energy, which is the sum of your potential initial energy plus kinetic initial energy, must equal the energy you're left with at the end, which is your final kinetic energy plus final potential energy. And these should be subscripts, the F and the I. I don't know, the subscripts have gone wrong here. So I'll correct that in the slides. That's the meaning of conservation. So the conservation of energy applies in this case too. When we are doing conservation of energy, we will typically ignore the potential energy due to gravity, because we already said the gravitational force is much, much smaller than the electric force. So we'll simply take the kinetic and potential energies for the charged particles and the charged interaction. So let's say we have two charges, Q1 and Q2, then one of them produces the field and the other one is in that field. And that's when we have the potential energy develop, right? So for potential energy, we need two charges. You cannot get potential energy with just one charge. So you can get a one charge can produce a field, but it cannot produce a force. One charge will have a potential at every point, but will not have potential energy. Yeah. In order to have energy, you need at least two charges. Sorry, the slides are just skipping around. We're going to come back. Yeah, we're back at this slide. This here is our formula for calculating the magnitude of the potential energy. So electric potential energy, K Q1 Q2 over R, okay? Not R squared. So this is one of the things that's very confusing about this chapter, that the formulae are very similar. The words are also very similar. Electric potential, separate from electric potential energy. U stands for electric potential energy. It stands for any kind of potential energy, actually. When you're talking about potential energy, you have to define where your zero is. In the gravitation case, we often took our zero as the ground. And here we'll take, for two charges, we're going to typically take the potential energy being zero at infinity. That means when they're infinitely far away from each other. And as you bring them closer, you then have some potential energy developed. Huh? And this is the magnitude of it. Okay, so let's just put some numbers to this. That's what's happening in this example. Determine the potential energy of two protons that are touching. So you basically have a proton and a second proton right next to each other, no space between them. The radius of one proton is 2 times 10 to the negative 15, is 10 to the negative 15. And since we have two radii, that becomes twice 10 to the negative 15. Yeah. So there we go. Here's our diagram. Here are the two protons touching each other. One radius is 10 to the negative 15. Second one over here, that becomes twice 10 to the negative 15. So that's the distance between their centers. This is K, 9 times 10 to the power 9. And then what's E squared? E is the charge on the proton, right? This time it's positive, the same charge as, same magnitude as the charge on the electron. So 1.6 times 10 to the negative 19. And then the second proton has exactly the same charge. So it's just written here as squared. Okay, that's my Q1, Q2, if you like. And if you put all this in your calculator, you're going to get this pretty small number, 10 to the minus 13 joules. Okay, now let's consider that we have more than 2 charges. So this was for 2 charges, but what happens if you take 3 charges, let's say, and you can join them up in the form of this triangle. So let's call them, say that we have equal amounts of charge, Q1, Q2, Q3, all equal Q, let's say. Then to find the energy of this configuration of charges, what does that mean? The configuration means this particular layout of charges, yeah? So if I want to change how these charges are, if I want to remove one of them or something, then I'm going to have to provide enough energy to break this potential energy that's binding them together, yeah, or holding them together. So what is the potential energy here? We'll have every charge interact with every other charge. Okay, so I need to take the potential energy between the interaction of 1 with 2 plus 1 with 3 and then 2 with 3. Okay, so 2 also interacts with 1, but we already took that, so we don't double count. Yeah? So you take each interaction only once. Luckily, energy is a scalar quantity, so no problem. We can simply add these up. We don't need to do any vector addition. We just do need to be careful of the signs of Q1, Q2. We are taking all of these as positive. So this is our expansion of each of these. U12 is given by Q1 times Q2, K times Q1, Q2, divided by the distance between them, which is R12, and so on for each of these. R13, R23, these might be different distances. So we have 3 terms here, okay? That gives me my net total potential energy, U123. Sometimes we call it U123. Sometimes we might just call it U3 for 3 charges. Sometimes we might just write it as U. So you need to understand that in context. Yeah? Okay, now we're going to do an example which has 4 charges sitting at the vertices of a square. And the square is of side L, so all of these are side L. So how many interactions do we have? We're going to look at that first. Remember, everything can interact with everything. So we want the potential energy of this configuration, yeah, of 4 charges. So I have my total potential energy term. I'm going to call it U4 for 4 charges. It can have 1 interacting with 2, 1 will interact with 3, and then 1 with 4. Then 2, it'll interact with 1, but we counted that, so we don't count that again. Then 2 with 3, plus 2 with 4, and then 3 with 4, and then we're done, because every interaction with 4, we've already counted. Okay, so now let's look at one of these. Let's say we look at U12, yeah? So if we look at U12, our formula was K Q1 Q2 over the distance, yeah? Not squared, just the distance, okay? If you square it, you're going to get the force. So it's just that distance to the power 1. The different distance between 1 and 2 is just L, and each of these is Q, so I can write that as KQ squared over L. Yeah, that's this first term. Anything, since all these charges are Q, anything else that's a distance L away will also give me exactly this value. So U13 is here, QQ squared divided by the same L, so that's exactly the same term. Yeah, so I'm going to put a little check mark above these. These are the same type of terms. Now U14, that's different. That's this diagonal distance. Let's call it R. So we can find R because each of these sides is L. So in this right triangle here, I took this right triangle, 1, 2, 4. R is the hypotenuse, so that becomes square root of L squared plus L squared, the 2 sides. And that gives me root 2 times L. Yeah? So that's the second term I need to write here. U14 equals KQ squared divided by root 2 L. Okay, so we'll put a different symbol here. U23. Now this also has that diagonal, so it's a similar term to this one. So I put the same sign. And then the other two are the same as the first U12. Okay, so we have 1, 2, 3, 4 terms, which are this much. So we get 4 times this. That becomes our first term here. Yeah, 4 times KQ squared over L. And then we have twice the second term. So 2 divided by root 2 is the same as just writing it as root 2. Yeah. So we get root 2 KQ squared over L from the second term. And then if we take KQ squared over L in common between them, then we have 4 plus root 2 equals KQ squared over L. So this is our final answer. And if you were given values for Q and L, then you would actually calculate it numerically. Okay, so here we're given values of Q and L, and we do the numerical. We just plug it into, this was our expression for the answer. And in here, we're going to plug in these numbers, and you get out the 0.97 joules. I'm not going to do this, but you can do this at home if you like. Okay, we're going to quickly do this one in the last few minutes that we have left. And this is a variation on what we did before. So we have the same 4 charges, and they're the same distance L away as before, but we added a 5th charge in the center this time, yeah? So we need to now find the potential energy for this configuration of 5 charges. I already know what it was for 4 charges. We just did it. So we're still going to have all those interactions amongst all those 4. So I have the total energy, U5, for 5 charges equals the combination of the 4, the potential energy from there, plus all the interactions with 5. So how many interactions can I have? So we have 5 with 1, 5 with 2, 5 with 3, 5 with 4, right? We have 4 of these, and they're all equivalent because they all have this same half the diagonal distance, yeah? And the same charges. So let's calculate one of those. First, let's find that distance R. Or maybe we call it D just to separate it from, we called the whole diagonal R before. So let's call this distance D. And in this red triangle that I've created now, D is the hypotenuse, and each side is half the length. So that's half of this length, and this is half of the vertical length, L over 2. So D squared equals square root of L over 2 squared plus L over 2 squared. That's going to give me D equals twice L over 2 squared, or root 2 L over 2. And that's the same as writing L over root 2. So root 2 goes into this 2, root 2 times. Right, so I can write one of these terms as KQ squared divided by L over root 2. So that's going to go in the numerator, the root 2. And then I have 4 such terms. So I need to multiply this by 4. And so that's what you see here. We have U4 plus 4 times KQ squared over L over root 2, or 4 times the root 2 goes in the numerator. And we can combine them, yeah? So we take out KQ squared over L in common, get another 1 root 2, that makes it 5 root 2.